AS Unit 1 Topic 8 is on the halogens. This is a specification for the topic, and we're going to start by looking at the colours of the elements and the trends in the group. We'll also look at their solubilities in water and in hexane. As we go down group 7, we change state from gas to liquid to solid. Each of these halogens have a specific colour. This is from the CS specification with the accepted colours for the halogens and for the halogens dissolved in water. Bromine has a boiling point of 59 degrees centigrade. So at room temperature, when we open a bottle of bromine liquid, we will find we get some bromine vapour, which has a red-brown colour. Iodine is a grey-black solid, and it is one of our substances that sublimes, which means it changes directly from solid to gas, and iodine vapour is purple. If we have a look at this table, this lists the melting and boiling points, the atomic radius, the first ionisation energy, and the electronegativity of the halogens. Previously in the unit, we have looked at first ionisation energies and electronegativities. So let's see, can we state and explain the trend down the group in terms of first ionisation energy and electronegativity? Pause the video if you want to try this question yourself. As we go down the group, the first ionisation energy decreases as we get an increased atomic radius and we get shielding by inner electrons, which means the nuclear attraction for the outermost electron decreases. In terms of electronegativity, down the group, the electronegativity decreases as the bonded electrons are further from the attractive power of the nucleus. The halogens are non-polar simple covalent molecules. The solubility of the halogens in water, which is a polar solvent, decreases down the group until iodine, which is virtually insoluble in water. A solution of chlorine in water is called chlorine water, and a solution of bromine in water called bromine water. If we look at this diagram, we can see the colours of the halogens in hexane and in water. So just to recap, halogens are non-polar covalent molecules, so halogens are more soluble in non-polar solvents such as hexane. We are now going to look at the reaction of halogens with cold dilute and hot concentrated aqueous sodium hydroxide. And we will look at the disproportionation in these reactions. We're now going to look at how the halogens react with alkali. You're going to have to learn all these equations. The first set of equations are with the halogen with cold dilute sodium hydroxide solution. When we react chlorine, we get a mixture of sodium chlorate, which is sometimes referred to as sodium hypochlorite, and sodium chloride in water. Bromine gives a similar reaction, and with iodine there is no reaction. These equations might seem familiar because we met them in the previous topic, the redox topic, as these are examples of disproportionation reactions. So we are sometimes asked to use oxidation numbers to show that they are disproportionation reactions. If we look at the ionic equations, you can see that the chlorine in Cl2 has an oxidation state of 0. The chlorine in the ClO- has an oxidation state of +1, and the chlorine in the chloride has an oxidation state of -1. Chlorine is being oxidized and reduced in the same reaction, so this is an example of a disproportionation reaction. The next set of equations that you have to know are the reactions of the halogens with hot concentrated sodium hydroxide solution. In this case, instead of getting the chlorate 1 ion, you get the chlorate 5 ion, where chlorine is in the +5 oxidation state. Bromine and iodine both react with hot concentrated sodium hydroxide. Again, in these reactions, we get disproportionation since our halogen is both oxidized and reduced in the same reaction.
So again, when we look at the ionic equations, we can see that the chlorine in the chlorine molecule has an oxidation state of 0, the chlorine in the chloride has an oxidation state of -1, and the chlorine in the chlorate 5 has an oxidation state of +5. So therefore, disproportionation has occurred because we've got oxidation and reduction of the same element in the same reaction. The final set of reactions we have to look at are the reactions of halogens with water. This is the equation for chlorine in water. When we bubble chlorine gas into water, we produce hydrochloric acid and chloric acid. Again, this is an example of disproportionation because the oxidation state of chlorine is both increasing and decreasing. Halogens are oxidizing agents. That means they need one electron to complete their full shell. Fluorine really wants to be reduced, so it is a really good oxidizing agent. Here are the half equations to show the reduction of the halogens to the halides. As we go down the group, the reactivity decreases, which means their oxidizing ability decreases. If we compare the halogens to the halides, we can see with the halogens, as we go down the group, the oxidizing power decreases. But if we now look at the halides, we can see that as we go down the group, the reducing power increases. Can you write equations for the oxidation of the halide ions? Pause the video and have a go. These are the examples where the halides are losing electrons to form the diatomic molecules. Let's recap. Halogens want to gain electrons, so they want to be reduced. Halides want to lose electrons, so they want to be oxidized. If you want to gain electrons, you're going to be a good oxidizing agent. And if you want to lose electrons, you're going to be a good reducing agent. However, as we go down the group with the halogens, they become less powerful oxidizing agents. And why is that? That's because down the group, the number of shells increases, there's increased shielding by the inner shells, so the attraction of the electron to the nucleus is weaker. With the halides, they become more powerful reducing agents as you go down the group. This is because the outer electron is further from the nucleus, so the outer electron has greater shielding by the inner electrons, so there's a weaker attraction to the nucleus, so it's more easily lost. The next section is where we look at displacement reactions. You've covered displacement reactions at GCSE. Now we're going to look at these reactions in terms of the oxidizing ability of the halogens down the group. You might remember these reactions as a more reactive halogen will displace a less reactive halogen from its solution. We use cyclohexane in these reactions as it does not mix with the aqueous solution and the halogen is more soluble in the cyclohexane layer, so we can spot what halogen is being produced. So let's have a look at reaction of potassium iodide with chlorine and potassium bromide with chlorine. In both cases, you can see when we added the solutions together, we got a colour change. If we now add cyclohexane, we can see that potassium iodide and chlorine water have produced iodine. And if we look at the chlorine water and potassium bromide on the right hand side, we can see that when we add the cyclohexane, it is clear that bromine is present. If we move on and look at bromine water, we can see that when we react with potassium iodide, we get a colour change, but when we react it with potassium chloride, we don't. So when we add the cyclohexane to the potassium iodide and bromine reaction, we can see iodine present in the cyclohexane layer. Finally, when we react iodine with potassium bromide or potassium chloride, we don't get a reaction in either case. So these are the results we would expect from our practical. You might want to now pause the video and see, first of all, can you write a balanced symbol equation for each reaction, and then can you write an ionic equation for each reaction? We have previously discussed how the oxidizing power decreases down the halogens. The displacement reaction of halogens with halide ions provides a clear illustration of the trends in the oxidizing properties of the halogens. So a more reactive halogen will displace the least reactive one from its compound. The next part of the halogens topic is to look at the reaction of solid halides with concentrated sulfuric and phosphoric acid. Let's recap the reducing power of the halides. As we go down the group, the halides become stronger reducing agents. That means that they want to be oxidized. So if we think about our chloride ion, it does not reduce sulfuric acid. Our bromide ion does reduce sulfuric acid, and our iodide ion also reduces sulfuric acid. And we would expect this because the halides become stronger reducing agents as we go down the group. The first reaction we're going to look at is the fluoride ion with sulfuric acid. If we look at this equation and we look at the oxidation numbers, it's not a redox reaction. That's because the fluoride ion doesn't have reducing ability. You will need to know the observations and the names of the products for this reaction. This reaction is not done in the lab because it is not safe to do so. The next reaction is a reaction of chloride with concentrated sulfuric acid. This is also not a redox reaction. The observations here are misty fumes of HCl, heat's released, gas produced, the solid disappears, and you get a pungent smell. The bromide ion is a better reducing agent, but the sulfur in sulfuric acid is only reduced from +6 to +4 in sulfur dioxide. Again, you're going to need to learn these equations and the observations for this reaction. When we move on to the iodide is a good reducing agent and is easily oxidized. It reduces the sulfur in sulfuric acid from +6 to +4 in sulfur dioxide, to 0 in sulfur, and to -2 in hydrogen sulfide. Again, you're going to need to know these equations, the observations, and the names of the products. This reaction has a rotten egg smell because we're producing hydrogen sulfide. Sometimes you might be asked how you would collect your hydrogen halide gas. This diagram shows the equipment that you would require. This is a recap of all the reactions with our halides and sulfuric acid. The specification also asks for the reaction of the halides with phosphoric acid. If you have a look at this slide, you can see that for each halide and phosphoric acid, there is only one equation. In these reactions, the concentrated phosphoric acid only acts as an acid. There's no further reduction of the phosphoric acid by the hydrogen halides, so you don't get a range of products that you would get with sulfuric acid. The final stage of the topic looks at the advantages and disadvantages of adding chlorine or ozone to drinking water. We've already seen this equation for bubbling chlorine into water. Here are the advantages and disadvantages. Finally, the advantages and disadvantages of bubbling ozone into water.